Good afternoon to you all. Permit me to stand on the existing protocols. My name is Abdulhakeem Yusuf, a lecturer from the Department of Mathematics, Federal University of Technology, Mina. And today, I will be delivering simple and ICTP research lectures in theory of partial differential equations. And this lecture is coming up at CRM exactly this time. Okay, thank you. Okay, so the course is broadly divided into 4 sections. We have the first section here, which is the first order differential equation, and then the second section, this course is broadly divided into 4 sections. We have the first section, which is first order differential equations. The section 2 is partial differential equations of second and higher orders, and section 3, second order differential equation 2, and section 4, we have the boundary value problem. So we hope and wish that we will be able to take 1 section per day. So that will take us from now till 30th, that's 27th to 30th, this same time. So before we move further in this course, permit me to motivate ourselves into why differential equation. As we all know, from time immemorial, there is one thing that has always been constant in life. And that thing is nothing but changes. And as long as this assertion continues to be true, then the study of differential equation can never be overemphasized. And as you all know, differential equation is broadly divided into 2. We have the ordinary differential equation, we have the partial differential equation. But our focus here is on the partial differential equation. And we are going to be looking at the first section today. We hope that we will be able to round up the first section before our time elapses, which is the first order partial differential equation. First order partial differential equation. Introduction. First order partial differential equation are equations that involve first order partial derivatives of an unknown function with respect to multiple variables. A first order partial derivative of a function u with respect to one of its variables, say xi, is the derivative of u while keeping all other variable constants. That is, supposing we are given a function and we are told to obtain the partial derivative of that function, what we do is to differentiate that function with respect to one of the variables while we keep the other ones constant. Then, a general first order PDE in 2 variables can be written in this form. Yes, if we look at it in this form of equation 1.1, if we look at it very well, we will see that in this equation, we have 2 independent variables, which is x and y, and then we have our u of x, y to be the unknown function, and we have the derivatives of this unknown function with respect to each and every one of these independent variables. So this, and then that is the u dot x and the u dot y are the first order partial derivatives with respect to x and y respectively. Then we have the types of first order PDEs. First order PDEs can be classified into various types, such as 1, we have the linear first order, we have the quasi-linear first order, and then again we have the non-linear. In the linear here, how do we recognize a linear first order PDE? Now let us look at what we have here in equation 1.1.1 here. If you look at it very well, we will see that this equation has 2 independent variables, which is x and y, and then we have the unknown function here, which is u. So here, the coefficients of these derivatives are a of x, y, b of x, y, c of x, y, and d of x, y, which is here, are given function of the independent variable x and y. So if you look at it very well, you will see that all this, you will look at all this, you look at this, we don't have any product here, we also don't have any product here. Then we have the second one, which is the quasi-linear first order PDE. A quasi-linear first order PDE has this form here. That is this form 1.1.2. In this form, the coefficient of the partial derivative can depend on the unknown function u. That is, here now, if you look at it very well, you will see that all the coefficients of the derivative only depend on the independent variable, which is x and y. But for quasi-linear, the coefficient of this derivative can actually depend on the unknown function u. And we have several examples of this kind of quasi-linear differential equation. Let's look at the Euler equation, which is given as u die x plus, let's say, v die u die x. Let's say everything here is equal to, let's just assume this. Let's say everything here is just equal to 0. If you look at it very well, sorry, this is die u die y. If you look at it, these are the derivatives. This is also another derivative. And this u here and this v here are unknown functions. So if you look at it very well, you see that what? You will see that if you are to compare it with what we have here in our 1.1.1, and mind you, this u is the same thing as u of x, comma y. So here, if we are to compare this, we will see clearly that our a here also depends on u, because u here is the coefficient of this derivative, and v here, which is also an unknown function, is also the coefficient of this. So this kind of differential equation is said to be quasi-linear. And then we have several others. We can also look at something like this. Let's say we have x. Let's say we have x die z die x plus maybe y die z die y to be equal to v. If you look at it very well, by the time you compare it to 1.1, you see that what? The d here also depends on what? On this unknown function. So this differential equation is an example of a quasi-linear differential equation. And then again, we have the third one. Sorry. We have the third one, which is non-linear first order differential equation. And we have this 1.1.3 here as the general form of the non-linear first order differential equation. Then derivation of partial differential equation. Consider the family of surfaces in 1.1.4 where a and b are constant and u is dependent on x and y, where x and y are the independent variables. So the derivative, to derive the partial differential equation PDE from 1.14, we eliminate the constant a and b by differentiating 1.1.4, that is the earlier equation here, this 1.1.4, we differentiate it with respect to the independent variable x and y. Then we have the following equations respectively in 1.1.5 and 1.1 and 1.1.6. That is, by the time you differentiate this given general form here, 1.1.4 here, we are going to obtain this 1.1.5 and 1.1.6. Then eliminating the constant a and b from these equations, we obtain a general relation of f of x, comma y, comma u, comma p, comma q. That is, the function is now going to change from this point here, which has a and b. The equation 1.1.7, that is this equation, is in general first order PDE if the number of constants to be eliminated is the same as number of the dependent variable and is of higher order if the number is greater than the number of independent variable. That is, if the constant to be eliminated in the differential equation are the same as the number of the independent variable, then it is first order. But if it is more than that, then it is of a higher order. But in this section, we are only going to be looking at the first order. Then let us look at this. Derivation. Consider the family of surfaces in 1.1.8, where phi here is an arbitrary differentiable function of f and g that are in turn known differentiable functions of some independent variable x and y, with u also a differentiable function of x and y. So by the time we differentiate this function here, which is given here in 1.1.8, we have this. we have this equation here. That is this one with respect to x. This one is with respect to y. And here we can take our du dx, our du dx here. We take this du dx here and du dy here. Look at them here. We take this du dx to be equal to p, and we take du dy here and also here to be equal to q. And that will give us this differential equation here. So you can see here we have taken our du dx to be p and du dy to be our q. So the differential equation has reduced to this. Now, if you look at this differential equation very well, we now say that eliminating diphi df and diphi dig, we have equation in 1.1.10. How do we do this? Or how do we come about this? If you look at it very well, if we are to eliminate our diphi df and diphi dig, we'll have to treat this differential equation as a system of equations. So what do we mean by that? Here now, this is what we have. We have this as the equation. We have diphi df in the bracket of df dx plus df du. Then we have p, close this, then plus diphi dig in the bracket of dig dx plus dig du. Then we have p here, and we say everything here is equal to 0. And then the next equation we have diphi df in the bracket of df dy plus df du dot q, then plus df dig in the bracket of dig dy plus this should be dig. Then here we have dig du. Then we have q, and everything here also is equal to 0. So if we are to eliminate this diphi df and diphi dig in this equation, all we just have to do is to transform this into a matrix form. So here now we can say that what this is the same thing as df dx plus df du. We have p. Then we have dig dx plus dig du. Then again we have p. Then the next one we have df dy plus df du. Then we have q. Then we have dig dy plus dig du. Then we have q. So we can just do this. We do this, and then here now we can have our diphi df and diphi dig. Then we have this, and we say everything here is equal to 0, 0. So this is what we have. Now, since everything here on the left hand side is equal to 0, then of course we can just say that the determinant of this matrix is equal to 0. So this implies that the determinant of df dx plus df du, then we have p, then dig dx plus dig du, then we have p. Then also here we have df dy plus df du, then we have q. Then here we have our dig dx plus dig du, then we have q. Then everything here we say it is equal to 0. And that is how we arrive at this our equation here in 1.1.0, because this is very crucial to our work. So equation 1.1.0 is equivalent to what we have in 1.1.1. Look at it here. So all we just need to do is, by the time we take the determinant of this, we are going to obtain this 1.1.11, where this p is taken as, we can actually move from here like this. We can actually take the determinant of this and equate everything to 0 so that we can see how we are going to obtain this, our equation in 1.1.11. So what are we saying in essence? Now, supposing now we decided to expand this. So, supposing we find the determinant of this and this. So we'll see from here that by the time we multiply this and this minus the and by the product of this and equate everything to 0, let's see how we can obtain this at 1.1.11 from here. So clearly we can see that there we can have di f di x. We can have di f di x. Then we have di g di x. Sorry, this should be dy. Di g di y. Then this multiplied by this again, we are going to have plus di f di x. Multiplied by that, we are going to have di g di u. We have di g di u multiplied by what? Multiplied by q. Then plus this multiplied by the whole of this. That will give us di f di u dot di g di y multiplied by p. Then this multiplied by this will give us plus di f di u multiplied by di g di u. Then we have pq. Then the whole of this minus this multiplied by this. So that also will give us, we're going to have di f di y multiplied by di g di x, then minus this multiplied by the other one will also give us di f di y, then multiplied by di g di u multiplied by di g di u. Then we have p. Then di f di u multiplied by what we have there also, that will give us minus di f di u multiplied by di g di x minus, then we have q, then multiplied by di f di u multiplied by di g, di u di x, then di f, this is supposed to be di y, di f di y multiplied by di g di u. Then we have pq also. So if we look at it very well, we will see that di u di f di u. Okay. So here we have, here now, we can now see that from here, we can now group all this together and see what we are going to have. So here now, we group this, and the first group we are going to have is going to be this and this, di f di x, di g di y, di f di y, di g di x. So this will just give us di f di x, di g, di y, minus di f di y, then di g di x. That is this and this. Then the next one now is now going to give us, here we have a di f di x, di g di u, di f di u, di g di x. So we can bring this and this together. We can see they all have a q in common. So we are going to have plus di f di x, di g di u, minus di f di u, di f, di u, then di g, di x. We can do this so that we have this. So that means this one and this one. We have them. Then now, the next one now we're now going to look at is now going to be this and this. So that will give us plus di f, di u, di g, di y, then minus di f, di y, then we have di g, di u. So the whole of this, we can see they all have this p in common. And then this one, di u, di y, then this, di y, this one, which is positive, and then we'll go with this one, which is negative. So everything here now is equal to 0. So now, we can now say this one, which is the coefficient of p, this one is the same thing as what we have here, which is di of f, that is fg, di of f, comma g, divided by di of, what are the variables? The variables are u and y. So we are going to have our, or we said y and u, anyone, y, comma u. Then we have what? We have p, then plus the next one, which is this. And here we have what? We have di of, what we have here is also f and g. So f, comma g, then divided by di of x, comma u. Then we have what? Then we have q, then plus this, which is equal to di f. So we can just take this. The whole of this is what we are now going to take as our r. So here now, we can now say that we are taking the whole of this as our capital P. Then we take the whole of this as our capital Q, while we take everything here as our what? As our R. So that is what results into this equation that we have here in equation 1.1.11. So here now, by the time we resolve this to P, capital P, it will give us capital P dot. Then here that we have small p, this, then plus the next one, which is Q, then multiply by small q. Then of course, this is negative. If we take it to the other side, this will become negative, while this one will become positive. So it's still the same thing. So we can still call it R. And that is how we obtain this equation here in 1.1.11, where our P is Q, where our P is this, Q is this, and R is what we have here. So let us look at a very short example just before we move further. This says that eliminate A and B from the following families of surfaces to obtain a PDE. And we have this example here. Look at the example. We have here x minus a all square plus y minus b square plus u square equal to d square. The first thing we are going to do here for us to obtain a PDE in this place is to differentiate this differential equation with respect to the independent variables. And we know that the independent variables here are x and y. So if you carry out the first derivative with respect to x, this is what we are going to have. And from here now we can see if you differentiate this with respect to x, we are going to have this. This one is going to be a constant. Then this one we are going to have 2u du dx, while this d is a constant, and then it will go to 0. So by the time we do that, this is what we are going to have. And then again, all we just need to do is to see that, of course, from our earlier assertion, we say that what? Di u di x is equal to p. So we can just replace this di u di x here with p. And once we do that, then we divide through by 2 so that we can have this equation. So x minus a here is equal to minus up. The same thing here, if we differentiate with respect to y, this is going to be a constant, it will become 0. While here we are still going to have 2y du dy Why this here goes to 0? Because it is the constant. So that is why we have this equation here. And everything here goes to constant, does the same treatment as we did to this first equation here. We divide through by these two so that everything here goes to 0. And then, of course, our du dy is the same thing as what? As q. So we just replace this du dy with q. So that gives rise to this equation here. And then from here also, clearly we can say that what? Y minus b is equal to minus uq. Now that we have obtained our x minus a and our y minus b, all we just need to do is to substitute back into this given equation. And once we do that, this is what we are going to have. Of course, we said our minus up is equal to x minus a, and y minus b is the same thing as what? Minus uq. So once we square both of them, just as we have in the given this, we are going to have p squared plus q squared plus 1. That is this u. If you factor this u out, because it's common to all of them, this is what we are going to have. And this equation 5 here is the first order differential equation. So that is that on derivation of a first order partial differential equation. Now let us look at the item 1.1.3 solution of Lagrange's linear equation. The general partial differential equation here in 1.1.13 here, this equation here, where this q and r are functions of x and y, is referred to as the Lagrange's linear equation. Just, of course, we have shown how we obtain this particular equation. So this equation is what we call the general form of the Lagrange's linear equation. Now let us look at this theorem. This theorem says that given this equation in 1.1.3, in which f of x, y, u is equal to 0 and g of x, y, u also equal to 0, constitute the integral curves of the simultaneous ordinary differential equations. So here we have dp divided by this, that is, from here now, we have our dx divided by dp is equal to dy divided by q and is equal to du divided by r. So then the general solution of 1.1 is given as what we have here in 1.1.16, where f is an arbitrarily differentiable function. Further, then we can have these w of x, y, u, assuming it's equal to c, is any solution also of the same given differential equation 1.1.13, and first order derivative of f and g, and these are all continuous. Then the solution w minus c will be equal to 0 is contained in the general solution. Now let us now look at this. Now differentiating the equation 1.1.14, that is where we have this. That's this equation. That's this equation that we have here. Supposing we differentiate this, of course we can see that f here is a function of x, y, and u. G also is also a function of what? X, y, and what? And u. So now supposing we now differentiate these equations, by the time we do that differential, this is what we are going to have. For the first one, we are going to have this derivative, and then the second one we are going to have this. And then again, by the time we take the integral curve, we are going to have this equation in 1.1.17. And then since 1.1.15 determines the integral curve of this, then we have from 1.1.17, then we can see that we have this. Now, considering any function relation where f is differentiable, then we have this equation. Of course, we can still remember this equation. This is where we started from, that we used to derive the general Lagrange's linear equation. So from here, we can answer it. Of course, if you come here, and then we eliminate the f, we eliminate this, and we also eliminate this, surely we are going to have this equation. We are going to have this equation. So here, this is what we have. We can see them. We can see the equation as derived earlier, which give rise to this. Now, consider any solution this, which is equal to c, as we have said earlier. Then differentiating this solution here with respect to x and y, it will give us this. Now, for this equation 1.1.22 here to be satisfied, this p will have to take these values. This is what it will take. P here will be equal to minus di omega di x divided by this This is what we're trying to say. That is, P here, P will have to be equal to minus this divided by dx, then divided by this upon u, and then again, Q will have to be equal to this divided by di y negative divided by di omega di u. So if we go back now and then we substitute them into this, of course, we can see clearly that here now we are going to have, that's di omega di x plus di omega, then we have di u, then multiply by what we have here as our p, which is giving us what? Which is giving us minus di omega di x. Then of course we can just change this as di u di omega. Okay, so by the time we do this, of course we know this will cancel this, and then this will surely go with this. Then you can see clearly that what we are going to be left with here is going to be di omega di x minus di omega di x, which is equal to 0. So same thing happens to the other equation, which is this. So on substituting P and Q and R, then we obtain this equation. So here now, if we now look at then, and in view of the relation 1.1.13 and 1.1.24, we have this particular equation. Now, what are we trying to say here? What we are trying to say here now is that, supposing now we come to this equation here, this equation here, then we bring in, of course, we know what our P is. We bring in our Q, we also bring in our what? Our R, then we carry out this particular expression. Everything here is going to be equal to 0. We can try it by expanding this, we expand this, and we also expand this. Everything here is going to give us 0. And once we have that, then we can now say that what? The Jacobian of this is equal to 0, since the partial derivative of f and g and omega are supposedly continuous. The vanishing of the Jacobian j in 1.1.26 implies a function relation of this form. Of this form here, hence this is equal to this, and by the time we take this back, this will be equal to g of f comma g, say, which is equal to 0, as we can see here. Therefore, the solution is equal to 0. So here, what we are trying to say here is that by the time we expand this, of course, by the time we expand this, this is this is what we have here, that of f comma g di u di y di u. This is the same thing as di f di y. We have di g di u minus di f di u multiplied by di g di y. By di g di y, then we say that the whole of this to multiply di omega di x, then plus the next one. The next one will give us di f di x multiplied by di g di u minus di f di u multiplied by di g di x. We can cover this. Then this will multiply di omega, then di what? Di y, then plus the next one, which is di f di x multiplied by di g di y minus di f di y multiplied by di g di x. So the whole of this will multiply di omega di x. So by the time we expand this, so if we look at it, we'll see that now let us see what we can actually have in this place. So here, by the time we expand this, we can see clearly that this is the omega di x, this is the omega di y here. So here now we can just expand this and see what we are going to have. Let's see. So here now, by the time we expand this, we say that we can see here we have di f di y di g di u multiplied by this, So let's see. Die f, die y, die g, die u, no? See? Sorry, this is die x. Then the last one should be, sorry, this is die u. This one still stand as, this one should stand as die y. Second one here is die y. Then we have this. So by the time we expand this, let's see. This multiplied by this will give us die f, die y, die g, die u, multiplied by die omega, die x, minus die f, die u. Then we have die g, die y. Then we have die omega, die x. That is the first expansion. Then plus the next one, which is going to be die f, die x, die g, die u, multiplied by die omega, die y, minus die f, die u, then die g, die x, die omega, die y. That's what we have. That's the negative. Then we can also expand this, which will give us plus die f, die x, die g, die y, multiplied by die omega, die u, minus die f, die y. Then we have die g, die x, then multiplied by die omega, die u. Then obviously this will give us 0 by the time we do the cancellation. This is what we are going to have. We can see clearly that everything here goes to 0. So that is how we show these the theory. Once we're able to prove this, then we have this. Then now let us look at the next item here, which is the general method for the solution of first order partial differential equation. Now we have been talking about first order partial differential equations since. The next thing we want to look at is how do we solve these differential equations. Of course, we have several methods. So here we are going to be looking at the general method for solving first order PDEs. And the first one we have the Chaptis method, and then the second one we have the Jacobi's method. We are not going to look into the applications of most of these methods, but rather we are going to give the theory because that is what the course stipulates. 1.2.1, that is the Chaptis method. Given the PDE in 1.2.1, since u is a function of both x and y, we thus have our du to be equal to p dx plus q dy. If we have another function f of x, y, u, p, q, a, you can see here now another constant has been introduced, which is a, to be equal to 0. Then it will be possible to evaluate p and q from the two equations, 1.2.1 and 1.2.2, in this form here. P equals to phi of x, y, u, a, and q also equals to this capital phi, psi of x, y, u, a. Substituting these values into 1.2.2 renders it directly integrable using some weighing function, and the integral, which is of this form, that is this form that we have here, will be a solution of the original PDE. So for the solution gives what we have here in 1.2.4, these two here. Then comparing 1.2.4 with 1.2.2, it means that what? Our fx divided by minus fu is equal to our p, and the fy divided by minus fu is equal to our q. That is, by the time we compare this with our Lagrange's first order differential equation. So from f of x, y, u, a to be equal to treating u to be equal to u of x, y, of course, which is the unknown function, then we have these relations in 1.2.6, where fx plus fu dot p will be equal to 0 and fy plus fu dot q will be equal to 0. This is just what we show in here, where we say that substituting the value of p, these values of p, substituting these values of p into these 1.1.22, these equations here will be satisfied. So the same thing happened here. So our p here, it implies that this is our p, this is our p, and this is our q. So p here is equal to phi and q is equal to phi, which means that this phi is the same thing as minus fx divided by fu, and this phi here is the same thing as minus fy divided by fu. So since p is equal to this satisfy 1.2.1, it does implies that f of x, y, u, a is equal to b is a solution of 1.2.1. Since this solution contains two arbitrary constants, it is therefore a complete solution of this. The problem now, therefore, is to determine the function 1.2.3, referred to as the auxiliary function. In doing this, we observe that the quantities u, p, q substituted into 1.2.1, 1.2.3 satisfy them identically. As a matter of fact, the partial derivative of f and g with respect to u, x, and y must vanish. So here now, by the time we carry out the derivative of f here, now mind you, our f that we are trying to look into here is a function of x, y, and u. G also is a function of x, y, and u. So by the time we carry out the partial derivative of each and every one of them, then we are going to obtain this. This is f with respect to x, g with respect to x, f with respect to y, g with respect to y. That will give us this equation. Again, if we eliminate our dp dx, as we have done earlier in the earlier session, we are going to obtain this equation. Same thing, that is from these two. Same thing from 1.2.9. If we eliminate our dq dy, that will also result into this equation that we have here, which is 1.2.11. Now, what happened if we now bring the two of them together? Bringing the two of them together now will now give us our Chapt's equation that we are looking for. And we should also note that this is interpreted as this because we have shown this earlier. Now, again, we need to recall that if we say that so here we say that, of course, we know that our q, we say that q is du dy and p is du dx. We know this. Now, let us now look at this. Dq dx. This is the same thing as dx of q, which is du dy. And this is the same thing as the squared u dx du, which is the same thing as, of course, it's only one unknown function that we have here, which is u. And as such, of course, the second derivative of this, we can easily interchange this. This is also the same thing as the squared u, then we have dy dx. And this is the same thing as dy of du dx. And this is the same thing as dy of du dx is p. So we can just have our p here. So it means everything here is dp dy. So it shows that what? Our dq dx is the same thing as dp dy. So that is what we have there. Now, let us now see, how do we bring our equations together. That is this equation here. We say that this equation is equal to 0. And also we say that this one is also equal to 0. Now let us now bring them together and see if we are going to obtain this equation 1.2.14. And for us to do that, let us now pick this our equation. Let us now expand this equation and let's see what that will give us. The first one, let me clean this. I have said it that let's keep this. Di q di x is the same thing as di p di y. So let us see the expansion of this. The expansion of this is simply di f di x di g di p, then plus minus di f di x di g di p, then plus p in the bracket of the expansion of this also di f di u di g di p minus di f di p di g di u, then plus di p di x then in the bracket of di f di q di g di p minus di f di p di g di q is what we have. Then plus the next one, which is going to give us di f di y. Then we have di g di q minus di f di q di g di y, then plus q in the bracket of di f di u, then we have di g di q minus di f di q, then we have di g di u. We close this, plus di q di y in the bracket of di f di p di g di q minus di f di q di g di p. Close this and we'll say everything here equal to 0. So this is what we have. Now, by the time we now expand this, let's say we are looking for the coefficient of, let's look at the coefficient of di g di p. Of course, we know that we can have this di g di p, and then here also di g di q di g di p. So Now let us now look at this. We have this. This is di F di X. And then here we have di G di P. Then here we have P. Then we have di F di U, di G di P. So we can bring this one and this one. We can bring them together. And by the time we bring them together, we are going to bring out the di G di P. That is this and this. And that will just give us di F di X, di F di X, then plus P. Here now we are going to have di F di U. We can close this. Then we have di G di P. Then we have di G di P. That's what we have there. Then we have, now let us look at di G di Q. Let's see di G di Q. So, okay, we can have this. Then let's look at the other one. We can have this and this. Let's look at this and this. So that there we have our plus. Then we have di F di Y. We have di F di Y. Then the next one there is going to be plus Q. Then we have di F. Then we have di U. Then we can close this, and then we have di G di Q. So we have di G di Q. Then plus, that is that for that. Now let us now look at the other ones. The other ones that is left. We have this, which happens to be negative. We have this. Then we have this. So let's see the ones that are common. Now let us see the one that have di G di U in common. Let's see. Of course, we have this, which is having di G di U. Which is having di G di U. Then we have, that's this. We have this particular one. Then we have this. They are both having di G di U. So we can just say that we have cleared this. So we can just say this. We have, because of this negative, this is going to be minus di G, minus di F di P. That's what we have. And then we have P here. And then here we have di F di Q. So that means we have minus di F. Then we have di Q. Then of course, because of this Q here, so we have another Q here. We can cover this. So that means this one is out. This one is also out. So let's see what and what are we left with. What and what are we left with? So taking care of this, then we are left with so let's see. These are minus di F di P, then di G di Q, di P, then di G di X. Then let's see. So here, let's look at the coefficient of di G di X. So let's see. So here we have this, which is minus di F, which is minus di F di X. But what we are looking for is minus di F di P. Let's see. Okay, minus the f di p, then we have our dphi dx, and then again, we should not forget that our di q di x is the same thing as di p di y. So here, we are now going to have our minus df, then we have dp, then multiply by di g di x, then plus another bracket of minus di f, then we have di q, then multiply by di g di x. Then we can say that what the whole of this is equal to 0. So by the time we expand this, so here now, from here, we can just take this is linear differential equation of order 1 that must satisfy 1 point, and then it integral are integrals of the Lagrange auxiliary. So we can just take the integral curve of this particular equation, which is this equation here. We can just take the integral curve of this equation. So that is what we have. And then this equation here that we have here, which is 1.2.15 here, are known as the Chaptis-Catillari equation. Any integral of 1.2.15 involving P or Q or both is taken for the required second relation. In fact, the simplest relation of this is taken as 1.2.3. And on obtaining 1.2.3, P and Q are determined from 1.2.1 to 1.2.3. And the value substituted into this 1.2.2, which on integration will obtain the required complete solution of the given differential equation. And this is the Chaptis equation. This is the Chaptis equation. And then we have the next one, which is the second method, which is the Jacobi's method. We are going to continue from where we stopped by looking at the second method, which is the Jacobi's method. In the last section, we discussed the Chaptis method for solving a PDE involving two independent variables, x1 and x2. The present method, Jacobi, is quite similar. It is expedient here to recall the following theory, which is very important from the elementary calculus. The theory stated that if this function, phi of x1, x2, x3, possesses a continuous partial derivative in xj, then phi 1 dx1 plus phi 2 dx2 plus phi 3 dx3 is an exact differential equation. If and only if we can establish these three conditions. So, supposing we have a differential equation in 1.2.18 explicitly involving the independent variable u, here we shall prove that 1.2.18 can be transformed into another differential equation with a new dependent variable, which does not explicitly occur in the number of the independent variable, increased by unity in the process. Then we shall rename the variables as follows. Here, we have x taken to be x1, y taken is supposed to be x2 here, and the u here is taken to be x3. And then introduce a new variable v, which is equal to v of x, y, u. We now consider these relation, where v of x, y, u is equal to 0. Then by assuming P1 to be equal to this, and P2 this, P3 this, then yield this differential equation. That is, by the time we differentiate this differential equation in 1.2.20 here with respect to these variables, we are going to have this differential equation here in 1.2.21. So, and then again, assuming our P is equal to minus P1 divided by P3, and Q is assumed to be equal to minus P2 divided by P3, thus V is equal to 0 will be a solution to 1.2.18 if and only if this differential equation is equal to 0. So clearly you can see that this differential equation has shifted from f of x1, x2, x3, and uv to f of x1, x2, x3, p1, p2, p3, which is equal to 0. So clearly the PDP in three independent these does not explicitly involve the dependent variable v, which ends the proof, as you can see. So this method applies to PDE of the form 1.2.3, that is PDEs that are of this form. We apply this Jacobi's method, whose central idea is to construct two more auxiliary relations of this form, G2 and G3, where Pj is this. Now, such that we have this relation. So whenever such function this can be determined, then there exists another function which is file 1 of x1, x2, x3, and a comma b, such that the file the x1 is equal to this, the file the x2 is equal to this, and the file the x3 is equal to this, where with Pj we have this. And the differential equation, this minus dv will be equal to 0, become the file minus dv equal to 0. That is the whole of this. This will become the phi. That is, the whole of p1 dx1 plus p2 dx2 plus p3 dx3 minus dv will now become 0. So, will become d phi. So, d phi minus dv is equal to 0, which then yield this. That is, by the time you integrate this, by the time we introduce the integral here, we integrate this, will give us phi. We integrate this, is going to give us v. When you integrate 0, we are going to have a constant, which is what we have here. So, we observe that from equation 1.2, we get back our 1.2.7. So P1 is given as this, P2, and then we have our P3. So then we can round them. Of course, we have said our Pi is equal to file I. So if P1 is equal to this, surely it is the same thing as file 1, the same thing as P2, the same thing as P3. Since by hypothesis this is equal to this, then constitute a solution, this for this. Then we observe that V is equal to file minus A. That is, by the time we take file to the other side, is a solution of this, which contains three arbitrary constants, A, B, C. Therefore, it is a complete integral of this. So if the original PDE is of the form 1.2.18, then we identify this and this so that V will be equal to phi minus A, and is a solution to this equation. Hence, V is equal to 0 for phi equal to A, which is also a solution. This implies that phi is equal to A and gives an A parameter family of a complete integral of 1.2. Sorry, the mouse is having problem. 1.2.18 with A and B arbitrary constant. Then the determination of this G2 and G3 that we have. So supposing we have these G2 and G3 as such that we can solve P1, P2, P3 from these and this in 1.2.26, then they become identities of if Pj are placed with phi j, so that their partial derivative with respect to xj vanishes independently. Hence, from 1.2.24 and 1.2.25, we have these equations. So here now, we differentiate our G2 and G3 with respect to x1, with respect to x2, with respect to x3. And that will give us these three equations, as we can see them here. That's what we have by the time we do that differential. Then eliminating the P1, the x1, as we have always done earlier, we try to eliminate the P1, the x1 from that equation. That is the equation we reduce to what we have here. That is, the first one will reduce to this, the second one will reduce to this, and the third one will reduce to this, as we have discussed earlier. So, and then again, we should recall that this is the G2, G3 of dxk minus pj is the same thing as minus the G2, G3 of the phi of d of xj pk. Then using these this in this yield this equation. That is, by the time we put together all these equations here, we put together all the equation here in 1.2.3, we are going to obtain what we have here in, sorry, the mouse is not working now. Okay, it's working now. So we obtain this by the time we put the three equations together. And we can see what we have here. We can see this, we can see this. So we are going to take, then this one here is taken to be our L, while this one is taken to be equal to M, and this is taken to be equal to N. So we can substitute them into this, and that will give us this equation here. That's what we have. Then these three here, this, and this, are then taken to be our G2 and G3. So taking them to the other side, they become negative. That is G2, G3 is equal to this. That is what we have here. Then by the time you take it to the next side, that is what we are now going to have, what we have in here. So similarly, similar computation gives what we have in 1.2.36. The same thing we are going to have here, we're also going to have in this place and here also. So supposing now that the solution Pj pi j makes the expression this to be equal to 0, an exact differential, then therefore L equals to 0, M equals to 0, and N equals to 0 identically. Then from equation 1.2.35 and 1.2.36 and 1.2.37, we get that G2, G3 equals to 0, G3, G1 equals to 0, and G1, G2 is equal to 0 also. So then we recall that hence Z is equal to G2 and Z is equal to G3 are two solutions of the PDE of Z, G1, which is equal to 0. And then we have this equation here. By the time we carry out the derivative, we are going to have this 1.2.38, but we must have this to be equal to 0. So observe that 1.2.39 is a first order PDE. 1.2.38 is a first order PDE in the independent variable xj, pj with corresponding auxiliary equation that we have here in 1.2.40. So the couple ODE above are the Jacobi's auxiliary differential equation. So this is the auxiliary differential equation for the Jacobi. Then further on Jacobi's method, here we show here that if G2 is equal to 0 and G3 is also equal to 0 are two independent integrals of equation 1.2.39 and are such that 1, G2, G3 is equal to 0 and 2, P1, P2, P3 are solvable from, then 1.2.23, 1.2.24, 1.2.25, 1.2.26, then these equations will render the expression P1 dx1 plus P2 dx2 and plus this an exact differential equation. First, we know that Z is equal to C is an integral form of 1.2.39, so Z is equal to G2, Z is equal to G3 are two solutions of 1.2.39. Thus, we have G2, G1 to be equal to 0 and G3, G1 to also be equal to 0. So consequently, on the hypothesis of this, then we have these equations to give us what we have here. What we have here, these three we have here, and then this is a system of linear homogeneous equation in the unknowns. So that is, by the time we put this equation as a system of equation where we have our L, M, and N as the unknown variables, this will just give us what we have here. That is, by the time we put it in a matrix form, this is what we are going to have here, which is 1.2.41. And then the Jacobian is 1.2.42. Then recall that from our hypothesis, P1, P2, P3 are solvable from these two equations here, from here to here, which implies that J is not equal, that is, the Jacobian is not equal to 0, and then also the determinant is also not equal to 0. Hence, the system this gives L equals to 0, M equals to 0, N equals to 0, which implies that this is an exact differential equation for this. And this is the success of the Jacobian differential equation. So that is what we have here. And these are the two broad methods. Then we can just look at some textbooks where we can actually see one or two applications of this method. Now, let's just quickly move into the next section of the course, which is a partial differential equation of second and higher orders. 2.1, we have the linear equation, the most general linear mth order partial differential equation is of the form 2.1. That's what we have here. A naught, the square u, the xm, plus a1, this a2, then to b, in which a, b, m, n, and c are all constant or functions of x and y. So from equation 2.1, a constant coefficient PDE is thus given as what we have here, where all the coefficients of this derivative are what? Are constant. All these are a naught, a1, a2 to am, b naught, b1 to bm. All of them are constant. So this is an example of a constant coefficient PDE here, in which this ai and all these one are all constant. So supposing now we set the derivative with respect to x to be our dp, and we set to be our d, and we set the derivative with respect to y to d prime, we can actually reduce this differential equation into what we have here. So here now we have reduced the d dx and d dy into d and d prime. So that differential equation has been reduced to what we have here in 2.4. Or we can simply write it as this is the general form, f of d comma d prime of u, which is equal to f of x comma y, in which this is a differentiable operator of order m. Then the corresponding homogeneous differential equation reduced to 2.4 is given by 2.5. So by the time we set this f of x comma y to be equal to 0, this differential equation will reduce to this. And this is what we call the homogeneous differential equation, because what we have on the right-hand side, because the right-hand side is simply equal to 0. So that is why we have that. Then definition. A differential operator f is said to be reducible if it can be decomposed into factors of the form this: alpha d plus beta d prime plus gamma, in which alpha, beta, and gamma are all constant. Otherwise, it is irreducible. That is, if you can reduce this differential operator into this format, then we say that this differential, we say that the differential operator is reducible. But if we cannot, then we say that it is what? It is irreducible. And then we have the method of solution for this second order differential equation. The solution of 2.4 is analogous to that of an mth order ordinary differential equation, in which comprises of a complementary function cf that contains m arbitrary constant and a particular integral pi that contains no arbitrary constant. So in this case, the complementary function is the solution 2.5, is the solution of 2.5 and the particular integral of 2.4. That is, by the time we solve this problem, all we just do is we bring together the particular integral and then the complementary to form the solution of the differential equation. So then the complementary function, in order to obtain the complementary function corresponding to the solution of 2.5, we recall this theorem from the elementary calculus, which say that if the differential operator f, the general solution of 2.5, that is what we have in here, is equal to 0, where m is a positive integer, is given as what we have here, 2.7 here. This equation and this equation, in which the function these are sufficiently differentiable arbitrary function. Then we shall show this proving by using the principle of mathematical induction. Here now, we look at it. What happened when m, of course, for mathematical induction, we are going to look at it when m is equal to 1, when m is equal to k, and when m is equal to, let's say, k plus 1, or maybe we say when it is equal to p, and when it is equal to when m is equal to p, and when m is equal to p plus 1. That's what we have. So for when m is equal to 1, when m is equal to 1, this is what we have for the equation. We set m there to be equal to 1. So that means when m is equal to 1, this is what we have. Alpha d plus beta d prime plus gamma of u equal to 0, which is just simply this. Of course, we know that our alpha is d dx, and d prime here is di u di y, and then we have this. So by the time we expand this, we simply have this differential equation, or we write it this way by taking this to this other side. And then this is a first order PDE with the corresponding Lagrange auxiliary equation. This is the corresponding Lagrange auxiliary equation. So here now, by the time we take these two pair here, this and this, to solve, that is beta, that is the auxiliary equation is dx alpha, which is equal to dy. Then we have beta, which is the same thing as du. Then we have minus gamma u. So by the time we pick these two, we see that this will just give us beta dx equal to alpha dy. So here now we can have our beta dx minus alpha dy to be equal to 0. So by the time we integrate this, all we are just going to have, if we integrate this with respect to x, this will just give us beta x, minus integrate this with respect to y, we are going to have alpha y. So by the time we have this, then we say that and we integrate this one, we are going to have just what? A constant. So we have beta x minus alpha y to be equal to c, where this c here is a constant. Also, that is this pair. Then we can pick another pair again, which is di u, that is this di u to be equal to this dx. So by the time we carry out the integral of this, of course, we know the integral of du is going to give us the u. And by the time we integrate this with respect to x, this is what we are going to have also. So here now, in order for us to eliminate this link, all we just need to do is just to take the exponential of both sides. And once we take the exponential of both sides, this is what we are going to resolve into. And then already we know that what? Our c is equal to what we have here. So we just bring it in. We just bring in our c, and that will just give us this equation, where phi here is a differentiable function, and this proves the theorem for when m is equal to 1. Then now what happens when m is equal to p? When m is equal to p, this is what we are going to have. And remember, what we are doing is mathematical induction. So we are going to assume that it is true for when m. We are going to assume that it is true for when this m is equal to p. Then now let us look at it now. What happens now when m is equal to p plus 1? Yeah, we know that this equation here, this is when m is equal to p plus 1, we can see, and the whole of this is the same thing as what we have here. So supposing we take this omega here, to be equal to this. So this, like this, is the same thing as this, because we can easily write because we have our alpha d plus beta d prime, plus beta d prime, then plus gamma, then everything to the power of p plus 1. This is the same thing as alpha d plus beta d prime plus alpha to the power of p, then multiplied by another alpha d plus beta, then we have d prime gamma. This is what we have. Then by the time we take this one to be omega, so everything here will just give us alpha d plus beta d prime to the power of p. Then we have this omega. So that is how we come about this particular equation. So now by our hypothesis, we say that this is also equal to exponential this from the summation of this, or we simply write it as what we have here. This alpha cannot be equal to 0, so that the equation will be what? Will be defined from here. So, and if that is the case, by the time we open this for our omega, this is what we have. By the time we expand what we have here, that will just give us this particular differential equation here, and everything will be equal to this. So now from here, of course, we know that this is just a first order linear partial differential equation with corresponding Lagrange's auxiliary equation, which is given as this. So here now we can now find the auxiliary equation for this, and that will just simply give us what we have here. And for us to do this, the first thing we are going to do is we are going to take these two pairs, and we know that by the time we take these two pairs, it will simply give us what we have here. By the time you cross multiply, then you integrate both sides, we will surely have what we have in this place. Then we are now going to take the other pair, which is going to be the x, the alpha, together with this. And that is why we have this here. And on having that, you can see what the differential equation is. That is why we have this. Then again, by the time we expand this, we have this. And then this, the whole of this like this is the same thing as taking the derivative of this. By the time you take the derivative of this, we are going to be back here. So everything here is equal to what we have in here. And then we have, by the time we can now integrate both sides of this equation so that this prime here can go, so that we can have what we have here, and then we have this integral in this place. So by the time we integrate this, we are going to have this next equation. And then the general solution is therefore what we have in this equation 9 here, and then we have our u to be equal to this, and then which is, we can see from here now that by the time we put this together, we are going to have our summation from r equals to 1 to p plus 1 and x to the power of r minus 1. Then we have this, and this shows that this theorem is also true for when m is equal to p plus 1. So that is how we have that equation. Now, so I will okay. So that is how we have sorry. So that is how we have that equation, which indeed complete the proof. Then we note that if the operator this is reducible, it will be seen that our f of d comma d prime exponential this will be equal to f of alpha comma beta exponential alpha x plus beta y. So therefore it follows that u is equal to exponential, u is equal to exponential alpha x plus beta y is a solution of this, which is equal to 0, if f of alpha comma beta is equal to 0. So in general, we have this to be equal to 0, gives a different pairs of solution this. So this way, we obtain different solution. For this, where Cj are constant, obviously the linear combination of this is also a solution. So indeed, the most general solution is of this form. And now, we have what we call, this will give us, everything we have done here is just for us to solve the left-hand side of the differential equation. Then what happens if the differential equation is an inhomogeneous differential equation? Surely, we are going to need what we call, the particular integral. So determine a particular integral pi of this. You can now see that the differential equation has now changed. Now what we have here is a differential equation of inhomogeneous type, where this f of x comma y is not equal to 0. So here we are going to see how to generate the particular integral in order to obtain the solution of this problem when the right hand side is not equal to 0. And we have I think we have prepared two methods on how to obtain this particular integral. So I would like to stop here. Yeah. Okay. So we'll stop here and then we'll continue from these particular integrals tomorrow. Thank you all for listening.